Meine Damen und Herren, ich hoffe, Sie erlauben mir nur 2, 3 kleine Worte. Auch Sänger sind wissenschaftlich. Also wir versuchen es auf jeden Fall. Zum Beispiel hatten wir in diesem Raum ein ganz tolles Oratorium aus der Barockzeit vom Institut der Alten Musik, von der MD, wo ich auch Professor sein darf. Aber ganz oft werden wir gefragt, ob wir nicht uns ein Thema ausdenken sollen für einen Liederabend zum Beispiel und ein Programm. Und ich habe heute Abend das Glück, dass der junge österreichische Dirigent Felix Hornbachner, der übrigens sein Debüt an der Volksoper in der Zauberflöte geben wird, wann? Im November, Anfang November, 8. November, glaube ich. Ja? Also schreibt sich es gleich auf. Wir sollen uns was überlegen, und zwar, aber dies war jetzt ganz, ganz genau gesagt, und zwar die 3 Themen, die mir gesagt worden sind: Magie, Goethe, Faust. Naja, finde ich sehr interessant und finde ich auch wahnsinnig wichtig. Und das Schöne über das schöne Wien ist, dass nichts an der Operette vorbeigehen kann. Und somit fangen wir gleich damit an. Und ich habe von der Akademie der Wissenschaften auch einen extra Preis zu vergeben, falls einer die Tiere und die Sachen, die ich jetzt nennen werde, vorwärts und rückwärts mir nachher erzählen kann, kriegt am Ende des Abends einen Regenschirm mit der Akademie der Wissenschaften drauf. Und oder Sie können sich auch personalisierte Sandsäcke für zu Hause mitnehmen. Also, vom Zigeunerbaron Aschmey über die Wissenschaft. Als flotter Geist, doch halb verwaist, hab ich die halbe Welt durchreist. Faktotum war ich heiß und wie bei einer Menagerie. Zum Walfisch bis zum Goldfasan ist mir das Tierreich untertan. Schmeichelt mir die Klapperschlange, demnach so streichel ich die Wange. Der Löwe liegt vor mir im Sand, der Tiger frisst mir aus der Hand. Der Bube nicht mit der Hyäne, dem Krokodil reiß ich die Zähne. Der Elefant trägt in der Schüssel mir den Salat mit seinem Rüssel. Ja, das alles auf mir, das kann ich und noch mehr, wenn man's weiß ungefähr. Sie ist nicht schwer, sie ist nicht schwer. Ja, das alles auf mir, das kann ich und noch mehr, wenn man's kann ungefähr. Sie ist nicht schwer, sie ist nicht schwer. Mit Raritäten reist ich dann als Akrobat und Wundermann, bis ich zuletzt Gehilfe gab, bei einem Hexenmeister war. In meinem schwarzen Zauberkreis zitiere ich Verse dutzendweis, bin passionierter Feuerfresser. Inzwischen tauchen schlug ich Messer. Ich balanciere Japanesen und schon bin ich da gewesen. Im Krankenspiel bin ich groß, im Beutelschlag grandios. Ich bin ein Meister von Bedeutung und alles ohne Vorbereitung. Ja, das alles das kann ich noch mehr, wenn es ungefähr. Sie ist nicht schwer, sie ist nicht schwer. Sie ist
Thank you very much, Michael Schade, for this wonderful introduction. We heard, as you said before, der Zigeunerbaron by Johann Strauss. And in the core and in the center of the Zigeunerbaron, there is a so-called Gypsy Baron. This is a gifted and well-traveled director. And to some extent, Michael, maybe this is similar to our speaker. I'm happy to welcome you here with open arms, but more about him later. I'm happy also to welcome, ladies and gentlemen, you here, representatives from the Boehringer family and the Boehringer Ingelheim Stiftung Foundation, from politics, research, industry, and economy. Today is a special day. Arias are being sung. A world-famous tenor is performing. And the mood is, despite the floods that hit our country and many people in Austria, the mood is a good one, because today is AITHYRA's birthday, the day on which we laid the foundation stone for a new institute, AITHYRA KI in the biomedicine. Who or what is AITHYRA? Apologize those who have already heard me speak today, half an hour before, but I must explain to the other ones, to the audience, where the name comes from. We ask artificial intelligence because we had no real good fitting name for this new institute. We ask artificial intelligence, and they gave us the following answer. AITHYRA could be the fictional daughter of Athena, the wise Athena, who had no children, and Asclepius, the god of medicine. So AITHYRA, which is fictional, could form the bridge between the wisdom of being open to new technologies and medicine. And that is precisely what is in the core of that new institute. So we are enthusiastic about the name and try it. The first two letters of AITHYRA is AI, so it's easy to put in your head. To found a new institute today is only possible because we received the largest research fund donated in Austria from the non-profit Boehringer Ingelheim Foundation. It's around 150 million euros, which will enable us to finance and operate that institute until around 2037. The city of Vienna will erect a new building due to the business agency into which AITHYRA will move in 2029. Until then, AITHYRA will be housed in the so-called Marx box in the Vienna Biocenter. AITHYRA is not a new allotment garden, ist kein neuer Schrebergarten. AITHYRA is open to cooperation, which will bring the specific tools and methods of IE to the city's life science sector. This is particularly important for me. The topic of AI in biomedicine is too big to deal with alone. We need much more cooperation in Austria and in Europe. One person will guarantee for this, namely for openness and scientific quality. That is Michael Bronstein, professor in Oxford, numerous visiting professorships in the best research institutions worldwide, and anchored in the startup scene beyond science. He is the founding director and will lead AITHYRA to success, I'm quite sure, together with the commercial director, Anita Ender. Welcome to Vienna, welcome to the Academy. I wish you all the best and much success. The actual introduction of Michael Bronstein will be done by someone who knows him very well. It is his twin brother, Alex Bronstein, professor at the Institute for Science and Technology in Klosterneuburg. I'm curious to see whether that is an advantage or a disadvantage to know so many details about the brother Michael. But before that, we will hear another Michael, Michael Schade, once again. Thank you very much for being here, and I wish all of us an interesting and stimulating evening. Mr. Schade, Sie kommen nochmals auf die Bühne. Dankeschön.
So we've had magic and utter knowledge. Sometimes you have to pretend a little bit of knowledge. And now I have something for you, because I was asked to bring you something from the poet Goethe, the most famous of German poets. And I have an antidote for you today, because the song is called Musensohn, and it is the son of the muse. And if I may pass on a knowledge that I have, that I give to all my students at the university, it is the most important thing in the world, and anybody who's anybody in business knows this, that if you follow your inner muse, the thing that makes you do something and at the end it perhaps looks like child's play, that is the thing that prevents all of us from having burnouts, from not knowing about what to do next in life. And it answers that little question of why am I here on this earth? I really, truly believe that. And not everything is easy, especially not for Franz Schubert, one of the most famous songs in the world I will sing to you today. And I can tell you one thing about that song. Goethe hated this song. And the reason he hated this song is because it's so good that he felt it distracted from the message. But the message is, I want to get out there into spring. I want to feel the muse. I want to feel youth. And at the end of the day, I just want to be at the bosom of it all. So, if you don't like that, there's probably something wrong with your inner soul. Let's do it. Durch Feld und Wald zu schweifen, ein Mädchen wegzupfeifen, so geht's von Ort zu Ort, so geht's von Ort zu Ort. Und nach dem Traktor reget und nach dem Maß beweget sich alles an mir fort. Und nach dem Maß beweget sich alles an mir fort. Ich kann sie kaum erwarten, die erste Blume im Garten, die erste blüht am Baum. Sie grüßen meine Lieder, da kommt der Winter wieder, sing ich noch jenen Traum, sing ich jenen Traum. Ich sing ihn in der Weite, auf Eises Länge und Breite, da blüht der Winter schön, da blüht der Winter schön. Auch diese Blüte schwindet und neue Freude findet sich auf bebauten Höhen. Und neue Freude findet sich auf bebauten Höhen. Denn wie ich bei der Linde das junge Völkchen finde, sogleich erreg ich sie. Der stumpfe Bursche bläht sich, das steife Mädchen dreht sich nach meiner Melodie, nach meiner Melodie. Ihr gebt den Sohn ein Flügel und treibt durch Tal und Hügel, den Liebling weit von Haus, den Liebling weit von Haus. Ihr lieben holden Musen, war ruhig hier am Busen, auch endlich wieder aus, war ruhig hier am Busen, auch endlich wieder aus.
Good evening, ladies and gentlemen. Can you hear me? So, first of all, thank you, President Faßmann, for the kind introduction. And I'm really a little bit emotional to be here. I think this is a great achievement. And tonight it is my really great pleasure to welcome my, I would say, lifelong collaborator and colleague and friend and partner and accomplice, my brother Michael Bronstein. Michael is a professor of computer science at the University of Oxford, where he holds the DeepMind chair in AI. And as you may have noticed, we are identical twins. And just to answer the very frequent question, yes, I'm the older brother by whole 10 minutes. So I could spend a great deal of time listing all Michael's achievements and accolades and contributions, but I'd rather spare you what may look like just a recitation of his CV, and I admit that I don't remember them all anyway. So instead, I'd like to share you some personal stories that you probably won't find on Google, episodes that offer a glimpse into our shared journey that began probably long before any academic titles or professional honors. And so you know whom you're admitting this institute into whose hands. Probably my earliest memory of our collaboration dates back to kindergarten. And like many children, we found that institution rather confining. And in search of an exit strategy, we quickly dismissed the most obvious plan, fortunately, because it would involve explosives. And I should say that our infatuation with chemistry would emerge only a decade later, and to our parents' relief, we actually traded all our handmade bombs and rockets for a fish tank. And our plan B was, however, somewhere more feasible, flooding the bloody place. And with the help of our grandfather's advice on flow and volume calculations, we set to work and were immediately caught by our teacher in flagrante delicto, so to say. And she caught us trying to cut a water pipe in the cellar with a toy saw. And to her perplexed question, why are you doing this? We honestly chanted in choir what seemed to be the obvious answer. We are trying to flood the kindergarten. And somehow this incident didn't discourage us at all. We just had to reroute our scientific exploration. And we had our fascination with geology that led us to pester every adult we knew for specific types of rocks. And an inspiration from science fiction stories about space travel and alien mutants made us perform our first experiments in biology. And I admit, without Helsinki approvals, we were not so strong in geography. And those experiments included, for example, attempts at suspended animation of insects by putting them into the refrigerator. And we also tried to see if UV radiation could trigger some strange mutations in our bugs. And my friendly advice, don't try that at home. So throughout our childhood and then adolescence, Michael and I pursued countless projects, of course, too many to mention here, from attempting to incubate chicken eggs without a chicken, or subjecting various household items to, how shall I say, our analytic methods, and of course in the name of science. And I believe that each of these experiments, whether successful or not, and however laughable, I think they characterize very vividly, so eloquently, Michael's creativity and passion for discovery, a passion that evidently continues until this day. And without further ado, it is my honor to introduce my brother, my partner in many adventures, and some might say my evil twin, Michael Bronstein.
Thank you. Thank you very much. Well, I should say that this is probably the first time ever that I remember my brother introducing me in a scientific talk. So today we had a meeting with the notary, and to the question whether I have any previous criminal convictions, I answered no, but probably I should have recalled the adventures in the kindergarten, and well, it's probably not too late. And I also have I also have the pleasure to have my wife here, who also doesn't often come to my talks, and probably these two people are my fiercest critics that I should be afraid of. So I thought that when I got the DeepMind chair at Oxford, I thought that I have the best job title in the world because it gives me a legitimate excuse to harass Google at every major machine learning conferences, coming to their booth and asking to finally give me my chair. And so far, as you can see, the only thing that they could offer are stools, which is obviously not the same thing. And when Demis Hassabis, the CEO of DeepMind, came to Oxford a few months ago to receive his honorary degree, we felt that obviously we must reciprocate. So we made Sir Demis sit for a whole hour on what he described afterwards as the most uncomfortable chair in his entire life. But today, officially, I have an even better job title, and now I can say that I serve the goddess of biological AI, AITHYRA, who, as you heard from President Faßmann, is an offspring from the unlikely union of Athena and Asclepius, the Greek gods of wisdom and medicine. And she's born today, so she's young and inexperienced. Otherwise, I'm sure she would have had a chat with her heavenly colleagues to send us slightly better weather, but that's hopefully will happen in the future. And this is really an exciting point of time. I think this is really a unique time in my career. I think these kind of events happen only once, and I'm very grateful to the Boehringer family, in particular to Mr. Christoph Boehringer and the leadership of the foundation, Stefan Formella, with whom, as I was, we were chatting. We met in London almost 2 years ago, and there, when everything was still hypothetical, that's where I got into this project, and here I am already in the official capacity, and Mark Wittstock, as well as obviously the Academy of Sciences, President Faßmann, Hubertus Schmidt-Veltens, and Martina, who couldn't come. She was not feeling well. But many people behind the scenes that made this project happen, and obviously my partner in crime, as using Alex's expression, Anita, who will be the administrative director of the institute. So, and of course, everybody that came here tonight, the students, the directors, the politicians, our wonderful musicians. Thank you very much for making this a wonderful evening. So I want this new institute to be the coolest and the most magical place and one of the most beautiful European cities. Who said that magic cannot happen in science, right? And I hope you will welcome this new partner and collaborator in the Austrian scientific family. And as President Faßmann mentioned, I think the use of AI to name this very special endeavor is very apt, because Greek gods have traditionally accompanied various disciplines of science, and even in modernity, they have never really lost their importance as guardians, protectors, and sometimes sources of inspiration for what might be often uncertain path into the future. So I'm sure that AITHYRA will be our reliable guide. Now, talking about AI, we hear a lot about AI in these days, right? And it's fair to say that it has already become, to some extent, part of our lives, right? Whether consciously through programs such as ChatGPT, or maybe behind the scenes through algorithms, technology that powers our search engines, our social media recommendation algorithms. I think this technology will very rapidly and very dramatically change entire spheres of life and work. But probably what I'm most excited about is the potential of AI and machine learning to turbocharge scientific progress and to a golden age of discovery. And I'm using here an expression from an Economist article from last year. And we have already seen recently AI to achieve breakthrough and significant progress in fundamental sciences that previously were simply impossible with traditional approaches. And this ranges from controlling plasma in nuclear fusion reactors that in the future might give us free and almost free and cheap energy, to predicting weather, discovering new class of antibiotics for the first time in the last 40 years, to even helping pure mathematicians gain intuition to prove new theorems. And I think now is really the right time to make a big bet on these technologies that potentially will change the very foundation of scientific research that we have known for centuries. So at the new institute, we'll be mostly concerned with the question, how can we transform the way biological sciences are done with the help of AI? And we want to drive the biological revolution in the next decade with the ultimate goal of improving human health. And we do want our research to also have tangible effect on diagnosing and curing diseases, developing new drugs, understanding better how biological systems work in our body, and also how they stop working when we might get sick. So we want to collocate biologists and computer scientists in the same place, so we learn from each other, we breathe the same air, we dream the same dreams, we work together on the next generation of both machine learning and experimental technologies. And in my view, this is a necessary condition that will lead to the next breakthrough in this field. And at this point, it's probably a little bit hard to tell where these breakthroughs will happen. So at this point, we're open-minded about what biological problems we want to consider. But what is important for sure, we would like to consider these problems from the perspective of AI and machine learning. So we'll likely favor problems in which it is possible to experimentally collect or maybe simulate large amounts of data, and where the problems themselves are likely to be amenable to machine learning solutions. So we actually had a very poetic beginning of this evening, right? So with Goethe, so I felt that it is necessary for me also to quote from Goethe. So I think he very nicely captured in these famous lines that I have to read in the English translation, one of the main challenges of biological AI, which is the problem of biological scales. And he beautifully wrote that, who traces life and seeks to give descriptions of the things that live begin with killing to dissect, he gets the pieces to inspect, the lifeless limbs beneath his knife, all parts but link, which gave them life. And this is really maybe a poetic description of a problem that we see. If we look at ourselves, we find that we are built of tiny molecules that live on nanometer scale, they interact at femtosecond time scales, and we go all the way to cells, to tissues, to organs that form organisms and populations, and they live at scales of meters and years. So we have more than 10 orders of magnitude of gap between these different levels of abstraction at which we can consider biological systems. And it is often the case that while we have a very good understanding of the laws that govern these tiny scales, for example, we can describe the system of atoms that form a protein molecule using the Schrödinger equation from quantum mechanics, these are the laws that operate at the larger scales that are much more elusive. And if we consider a typical small molecule drug, we'll typically find something on the order of tens of atoms, and we can simulate such systems very accurately using quantum mechanical models like DFT. But if we go to larger molecules, a typical protein, for example, it will already contain maybe tens of thousands of atoms, and quantum mechanical models do not scale at all to these large systems. So we'll need to use models that operate at a different level of abstraction based on different principles, such as, for example, molecular dynamics. So a typical cell will contain 10 to the 14th power, or 100 trillion atoms, and I'm not aware, probably nobody in this audience thinks that it's possible to simulate computationally these kind of large and complex systems, and this is just one cell in our body. We have trillions of them. So what we see is that at each biological level, it requires its own level of abstraction and its own set of laws, and I think it was very aptly put by Philip Anderson, a Nobel laureate in physics, in his famous 1972 article that he titled "More is Different," and he wrote that the ability to reduce everything to simple fundamental laws do not imply the ability to start from these laws and reconstruct the universe. Instead, at each level of complexity, entirely new properties appear. And the problem is that at higher scales, we often don't have a good understanding or description of the laws that govern these scales. And this is really a fundamental problem in traditional computational science approaches, and probably more generally in computer science and software engineering, where the very foundation, the very premise is that we must a priori know the laws that govern our system, so we can write them in the form of mathematical equations and implement in software as a set of logic instructions that a computer can understand. And when we have programmed this software, we can apply it to input data to produce the desired behavior of the system. So this is how most computational science works. AI systems, on the other hand, work in a very different way, and this was really a paradigm shift that Andrei Karpathy, a famous AI researcher, called software 2.0. So AI is programmed not by feeding the machine with instructions, but rather by feeding it with data and desired behavior. So we reverse, in a sense, the directions, and from these two inputs, it can then infer or extract the right logic to solve the problem on its own. if it's, of course, given enough compute and the suitable optimization algorithm. And the logic, this logic is stored implicitly. So it's typically in the form of neural network weights, and the resulting algorithms act as a kind of a black box, a sort of implicit instructions that are usually not human understood. And I know that the term black box is often used with a negative connotation, but it was exactly this shift from handcrafted features and instructions to model-extracted black box features, really one of the defining characteristics and reasons for the success of deep learning models. Now, let me give you a simple example. So, simple task, you're given an input image and you want to tell if it's a cat or a dog, right? So, my 2-year-old daughter can do it without making any mistake. And yet it's very hard to define mathematically what makes a cat look like a cat, right? Or a dog like a dog. And in computer vision, literally decades of works were dedicated to creating very complex and smart ways of describing images with some handcrafted features. But deep learning came and made a completely different approach. Basically, while it's hard to tell what makes a cat look like a cat, it's easy to find examples, potentially millions of examples of cat images. And when we can then feed these examples into a black box that somehow will figure out on its own the right features to extract from the images that would be appropriate or optimal for this task. So mathematically speaking, this black box is a parametric family of functions, and the training examples of cats and dogs are samples of this unknown function that we are trying to approximate. And the goal of learning is to find such a set of parameters, right? You can think of them as knobs on this black box that will fit well the training samples. And when we are shown a new example of a cat and a dog that we have never seen before, it would be able to correctly classify it. And this is what we call in machine learning generalization. Now, artificial neural networks that are the foundation of deep learning that initially were developed in the 50s and maybe even some examples before, they are developed initially as a very highly abstracted model of how the brain works. In fact, the brain doesn't work in this way. But these are really examples of these kind of parametric functions that can be used for a variety of visual pattern recognition tasks. And what we know about these systems is that they're very general. So they have what is called the universal approximation property. So I can take any continuous function and under some mild technical assumptions represent it to any degree of accuracy. So basically this black box can do anything, right? The question is, of course, is how it can do it in practice. And the problem that we immediately run into when we try to apply it naively is a problem that is called the curse of dimensionality. So the number of images of cats and dogs that we need to show to a neural network when we work with data that lives in high dimension, and typically we work with data that lives in 1,000 or even million dimension spaces, will be by far more than the number of atoms in the universe, right? So we have exponential scaling laws that do not work in practice. So historically, the way to overcome the curse of dimensionality actually came from work in neuroscience. So the duo of professors at Harvard that went on to get a Nobel Prize in Medicine for the study of the visual cortex of the brain in mammals, they discovered that the neurons in our brain that are responsible for perception of visual objects are not connected in an arbitrary way. So they're connected very specifically, so there is local connectivity that is called the receptive field, and the weights or the activations of these neurons are shared, and this inspired a new class of artificial neural network architectures, initially developed in Japan by Kunihiko Fukushima, and later by Jan LeCun in the US, who also worked for a company called Bell Labs, where he also had access to the early digital signal processors that appear to be a very appropriate hardware platform to implement these architectures. So what was special and what allowed to break the curse of dimensionality in these architectures was a property that we call translation invariance. Basically, when we try to detect a cat or a dog in an image, we don't care where it is located, right? So it's sufficient to say that it's a cat, no matter where it is. So computer vision researchers in the first decade of the 20th century somehow snobbed these methods and preferred the handcrafted features, and entire careers were made out of these very smartly engineered detectors. But everything changed at the beginning of the second decade of the 20th century, in particular in 2012, where it was for the first time that the compute power was sufficient to build sufficiently large and complex neural network architectures and also feed them with data that would allow to completely surpass anything that has been handcrafted, and this entirely changed all the landscape in this field. And I'm of course talking about the famous ImageNet dataset that was developed by Fei-Fei Li at Stanford, and the in a sense, reincarnation of convolutional neural networks, the famous AlexNet developed in Toronto in 2012. That was the breakthrough. And the rest, as they say, is history. So the Turing Award, the biggest prize in computer science in 2018, went to Jan LeCun, Geoffrey Hinton, and Joshua Benjoff, who were one of the proponents of these methods. And this created multi-billion industries. So the science in many fields doesn't look anymore like it used to be with the use of these methods. Now, going back to biology, let me give you an example of a typical problem. So people that come from biotech industry or pharma are probably familiar with. So virtual drug screening. I give you a molecule and you want to predict some of its properties. For example, whether it will be toxic or can you dissolve it in water, right? So here are the molecules, probably everybody will recognize it, right? So this is a molecule of caffeine that we all drink and like. And you can represent it as a graph, right, where the atoms are the nodes and the chemical bonds are edges. And in order to feed it into a neural network, I need to represent it as a vector, right, as a collection of numbers that represent, for example, the types of the atoms that we have in this molecule. So one of the issues that we find is that we don't really have a way or a special way to order these atoms. So any permutation will do. But of course, the properties of the molecule do not change based on how we order its atoms, right? So we need a property that is called permutation invariance. The neural network must be able to deal with any arbitrary ordering of this input. Now, we also know that molecules are not just abstract graph, right? So these are three-dimensional objects, right? So they live in some three-dimensional space. So every atom has three-dimensional positions. We can also rotate and translate molecules. We want to guarantee that the properties that we predict will not be affected by these transformations. So I guess you get the idea. Basically, we are asking the question, can we bake into our neural network architecture some properties that will define how it interacts with certain types of transformations that our input objects can undergo. And this is really the foundation of what we call geometric deep learning. So this is my field of research. I think I can probably take the credit for making up this term. And there is a zoo of different neural network architectures that were born based on these principles. And these principles are very antique. They are very old. And this is the notion of symmetry. And symmetry, as wide or as narrow as you may define its meaning, is really this one idea by which, through the ages, we try to comprehend and create order, beauty, and perfection. So I'm quoting here from Hermann Weyl. He was one of the most important mathematicians in the 20th century. And the term itself is much older than Weyl. It's much older than modern science. It goes back to ancient Greece. So Plato, for example, was a big fan of symmetry. He believed that these symmetric polyhedra, nowadays we call them Platonic solids, were so perfect and so beautiful and so nice that our entire universe must have been built out of these tiny polyhedra. And you think of it, it's not exactly a crazy idea because nowadays we know that crystals are organized like this. And Plato believed really that geometry is the most important type of science. According to a legend, an inscription on the entrance to his academy read that nobody who is ignorant of geometry is allowed to enter. I don't know whether it's true or not, but I definitely am a big fan of geometry. And geometry itself, that we still probably still teach at school as the geometry, it also goes back to ancient Greeks, the Euclidean geometry, right? That was based on, as you probably know, 5 axioms or postulates, one of which stood out. That was the postulate about parallel lines, which generations of illustrious mathematicians tried to prove or disprove to no avail until the beginning of the 19th century, where suddenly came the realization that you can construct self-consistent geometries that do not resort to this assumption of the postulate, the 5th postulate of parallel lines. And it created a zoo of different types of geometries, basically shattered the entire foundation. What is actually a geometry, right? So mathematicians couldn't agree or understand. It required a paradigm shift, and this paradigm shift came from a young mathematician. He was only 23 years old when he got the chair at the University of Erlangen in Germany, and as it was customary then, and probably still customary, he was asked to deliver an inaugural lecture, like the one that I'm delivering here. And it entered the history of mathematics as the Erlangen program, and it suggested a very radically new approach to defining geometry, which is looking at the objects and what happens to them when you subject them to different transformations. So mathematically, it was formalized using group theory, but basically it allowed us to study properties based on the symmetries of the objects. And this idea was very foundational in, it had a big impact in different fields of mathematics, but probably the most important impact was in physics, where in the beginning of the 20th century came the realization that actually we can apply these principles to our universe. So we can try to derive the laws that govern our universe from these first principles of symmetry and invariance. And probably the most famous result in this domain was the theorem proven by Emmy Noether, who showed that conservation laws that previously were considered empirical could be derived from first principles of symmetry. So, for example, conservation of energy could be related to symmetry of time. And the evolution of these principles and these ideas has led to our modern physics, which, again, I will quote Philip Anderson, who said that it's only slightly overstating to say that physics is the study of symmetry. And indeed, if you come from this field, you will probably know that more or less anything that we know and understand in physics can be derived from symmetric groups. So physicists like to talk about external symmetry, what is called a Poincaré group, that gives rise to the Minkowski geometry of space-time and special relativity, and the internal symmetries of quantum fields that create different forces or different interactions between particles. So you can see that there is a lot of similarity between this very global view of physics and how it governs the universe to our little and naive example of molecular property prediction. We also have an external symmetry, right? The symmetry of the domain, basically, in this case, the permutation of the nodes or the atoms in the graph that we wanted to be insensitive to, or the internal symmetry or the symmetry of the data. These are the rotations and translations of the molecule in space. And you can design special neural network architectures. They're called graph neural networks or transformers, which implement and respect these symmetries. And probably the most prominent and the most famous example of such architecture was AlphaFold 2. So that was a program from DeepMind that solved, at least to some extent, a long-standing holy grail problem in structural biology. And this is the problem of protein folding. So if you are not familiar with proteins, I was asked by my son once what I'm working on, and I took his toy, so with his permission, I have it here. So this is a protein, right? So it's a one-dimensional sequence of tiny building blocks called amino acids. So technically speaking, it's a biopolymer. So it's a chain of amino acids that are connected in sequence, right? So one-dimensional object. But because of electrostatic forces that act on these atoms, you can fold it into many different shapes, right? So I can take this one-dimensional thing and basically create more or less anything that I want out of it, right? And this three-dimensional structure is really what endows the proteins with their function, because a good analogy here is the analogy of a lock and the key, right? This metaphor that when you have a lock, there is only one key that will fit and will open it. So same way the protein surface, it's a three-dimensional object that will accept only one binder that will interact with it and enable some chemical reaction. And proteins, why proteins are important? Because that's basically the foundation of our life, right? So we don't know any life that is not based on proteins. They are everywhere in every biological system, whether it's transporting oxygen to our cells, defending us against pathogens, even making chemical reactions in our body possible. Enzymes are the enablers of catalytic reactions. So in the 70s, it was postulated by Anfinsen, Nobel laureate in chemistry, that the three-dimensional conformation of proteins is entirely determined by the amino acid sequence, and therefore there was a competition that was set where scientists every 2 years tried to come up with a better approach to predict the three-dimensional structure of the protein given its amino acid sequence. And what happened was a kind of ImageNet moment in structural biology. So a newcomer, a new player, computer scientist from a company called DeepMind that never worked on proteins, came and were able to beat by far anything else that existed in the field. And I'm talking about the famous AlphaFold, and probably I cannot say that the rest is history, because history is being made and being written in these days, but it is very likely a Nobel Prize level achievement. So I guess Demis Hassabis and his team eventually will get it. So far they got many prizes, including the Breakthrough Award. And from my perspective, I think it was also a very good example and a triumph of these geometric methods in machine learning. So it would be actually very, I think, pedagogical to look at these two breakthroughs that happened in AI. So one was the performance of AlexNet on ImageNet in 2012 and AlphaFold 2. So the paper appeared in 2022. So it's very easy, exactly 10 years separating these big achievements. So there is this maxim in AI and machine learning community that in ML, data trumps algorithms. So if you have a good data, then machine learning is easy. If you don't have good data, then you need to work hard. And I think it was first argued by Alex Wissner-Gross. So he looked at the time it takes from the introduction of an algorithm to the breakthrough compared to the time it takes from the introduction of the data set on which the algorithm was trained to the breakthrough. And you can see that in the past, it was the case that it takes much less time from the data that comes. This was definitely the case with AlexNet 2012. ImageNet benchmark was introduced in 2010, versus convolutional neural networks are known from the late 80s. It is interesting actually that the trend is reversed with AlphaFold. Now, take it a little bit with a grain of salt. So the methods are probably not exactly the same, but the data on which AlphaFold was trained existed for decades. The algorithms were relatively new. So I'm talking about transformers and equivariant architectures. And also the amount of data on which AlphaFold was trained was tiny by machine learning standards. So it was even an order of magnitude smaller than the predecessor 10 years ago, AlexNet was trained on, right? We're talking about just a few hundreds of thousands of protein structures. And this is obviously dwarfed by the humongous amounts of data on which programs such as ChatGPT are trained. So we're talking about probably trillions of data points. So there is something in the problem itself that makes it amenable to machine learning. And it's interesting to try to understand what is actually the recipe for success of ML in these kind of problems. Now, I know that this is very arrogant to make this claim that I know what makes ML successful. Otherwise, I would be working on the right problems. And I think that's one of the challenges of our new enterprise. But I think it's probably we can agree on a few common traits that we've seen in the past. And this is availability of large and diverse data sets with clear performance criterion. It's the presence of some internal structure in our data and what we can call degenerate solution space. So let me explain, starting from the obvious, right? The availability of large and diverse data sets. So in case of the breakthrough in computer vision, it was ImageNet. It was a benchmark established in 2010. It had more than 1 million images that were manually labeled by humans, exploiting, at that time there was a special service run by Amazon called Mechanical Turk. And it had 1,000 of different fine-grained categories of images. So not only telling apart cats and dogs, but how about telling apart Persian cat from a German shepherd dog. And the performance was evaluated as average test accuracy. So very clearly defined data set, very clearly defined criterion. So the same thing was the CASP, the critical assessment of protein structure prediction competition, the one that was won by AlphaFold. So it was established in the early 90s, and the data came from the protein database that itself was established in the 70s. And the amount of data that was available to AlphaFold initially was about 140,000 protein structures. And the performance criterion, again, was very clearly defined. It was median reconstruction accuracy, so the error in three-dimensional coordinates that you predict. Now, the second important ingredient that we find in many machine learning problems is the generate solution space. And if we look at images as points in some high-dimensional space, right, so we're talking about our images that cats and dogs abstracted mathematically as vectors, we find that they don't occupy the entire space. They somehow tend to cluster around a low-dimensional structure, which mathematically can be described as a high-dimensional surface or a manifold. So it is actually called the manifold hypothesis. So the data has low intrinsic dimensionality. If we take some random noise images, they will not lie on this manifold. And there are many reasons why this happens, but in natural images, what we find is that they're self-similar or compositional. So I can take a cat and take pieces of the image of the cat and piece them together. So I can take, for example, an ear and rotate and translate it. So images can be composed out of smaller pieces. And this is also the case, apparently, in proteins. So when you talk about proteins and people try to impress you, they will say that in theory you have something like 10 to the power 300 of possible proteins. So just to give you an idea of how big this number is, the number of atoms in the universe is 10 to the power 80. So we have hundreds of orders of magnitude between, right? So this number is totally unimaginable. But the question is whether all these possible, in theory, proteins are really materialized. And the answer is probably no. And what we know, that proteins that don't just come up randomly, they are result of evolution. And it appears that nature likes reusing existing solutions. So it is very lazy. When it found something that works, it will tend to use it again and again. And one good example, probably one of the most beautiful protein folds, is what is called the Tim-Barrel structure. So it's very ancient protein fold. It appeared probably more than 3.5 billion years ago, when our predecessors were still single-cell organisms. And it appears as a collection of copied and pasted what is called beta-alpha structures. And we see that it's heavily used, and it appears in 10% of enzymes that we know, and also across different functions and across different organisms. So we can find these folds in bacteria, or in our own body, or even in tomatoes, right? So it's really ubiquitous across functions and across organisms. The last thing that I want to mention is internal structure in the data, right? And here probably appropriate illustration will be from the domain of natural language. So let's do the following exercise. So I give you this sentence: bison grazed on the of the river estuary, right? And you need to complete the sentence, complete the missing space, right? So my son in his 6th year of school does it without any mistakes, and this is how programs like ChatGPT are trained. So now imagine examples of these sentences, but think of billions or maybe even trillions of these. So this is called masked loss, and to learn to do it properly, you will learn not only the grammar of the language, right? So you need to put the right conjugation, for example, of the word, but also the semantics, because here only one word will be correct, and which word to put is determined on the context. So programs like ChatGPT, they look at the context of a word and try to fill in the blank. We know, for example, that the word blank is polysemos, so in another sentence like this, bank will mean something else, right? It will mean a financial institution, and how do we know it? Again, from its context. So this internal structure of language is called distributional hypothesis, and it tells us that words occurring in the same context tend to have similar meanings. And this seems to be also the case with biological data, with proteins. So in proteins, this is captured in the form of multiple sequence alignment. If we look at organisms that evolve differently, but they're somehow related, it is very likely that they have proteins that have similar function and similar sequences. So we can use sequence alignment algorithms to basically match them and see whether the structures are the same. And what happens is that this relative placement of different structures, right, or domains, or amino acids within domain, are mostly predetermined by the protein's function. And because AlphaFold is trained on functional proteins, right, that survive the evolution and appear in organisms, it's provided with very strong signal to learn the distributional hypothesis for protein sequences and structures. And we can conclude that AlphaFold is a convincing example that machine learning can work for the right kind of biological problems, if in the right setting, and there are really good reasons for it to stand out as a particular breakthrough in biological AI. It's both the nature of the data and also the nature of the problem, right? So all the characteristics that we have described. Now, it might be the performance of AlphaFold is not due to its generalization capabilities, but quite the contrary, because it doesn't need to generalize. So you can likely solve protein structure prediction problem without really having to learn any laws of physics. And there is actually evidence that to fold new sequences, AlphaFold, what it does essentially, it just retrieves a rough set of global domain or motif arrangements and then just pieces them together. And I think this brings us to an interesting question, maybe a philosophical question and subject for a different discussion, whether in the age of AI, science itself might not look very differently. And there are these maybe wild conjectures of post-theory science, right? So some claims like this provocative article that appeared in The Guardian about that we are on the verge of post-theory science, and she writes here that so much data had accumulated and computers are already so much better than us at finding relations with it that soon all scientific methods of hypothesize, predict, and test would be relegated to the dustbin of history. Now, AlphaFold is actually a good example because it produces accurate predictions of protein structure that we can test experimentally, but it's a black box that doesn't really offer us a theory of protein folding, or at least it doesn't offer a theory that human scientists can understand. And if we believe in this future of science, where increasingly larger parts of the hypothesis generation will be taken from the humans to the machine, an obvious question would be to ask whether the experimental technology that feeds the data into these methods is adequate. So in other words, when the main consumer of the data is increasingly the machine, do we still need to stick to data sources that were developed originally with human scientists in mind. And with my collaborator, Luca Neff, we wrote an essay where we argued that the most significant future breakthroughs in biological AI will likely arise from the transition away from traditional, what we call white box data, understandable by humans, to novel, high throughput, low cost, AI specific data modalities that we call black box. So these are modalities that will be developed in tandem with appropriate machine learning methods. And to give you an example, so historically in traditional biological research, also in pharma and biotech industry, again, at least traditionally, the data was collected by human scientists for human scientists, and it was analyzed by human-designed algorithms based on their best understanding of the problem, right? So protein folding, again, is a good illustration. Early methods were first principle, physics-based, white box software 1.0, right, that was applied to crystallographic structure data collected by biologists, again, white box data that humans understand. So the next step was to replace the white box software with black box software, such as deep learning methods that produce better results, but we, in exchange, we lose some understanding of how these methods work. And again, AlphaFold is a good example, but it's still trained on white box data, protein crystal structures that were collected by structural biologists starting from the 1970s. And I think that applying ML to existing data modalities as some kind of magic pill is not necessarily a good fit. And in fact, many examples of, for example, biotech companies of that generation so far have shown limited success. And when you hear people saying that, oh, AI in biology is overhyped, I think it's usually this kind of stuff that they have in mind. So the one logical step, right, the next generation of ideological approaches in biology, you can think of them to produce data systematically in a way that would be consumed for machine learning, basically scaling existing experimental technologies. And these approaches have shown some success in biotech industry. One example is DNA-encoded libraries, companies like In Citro, or cell painting. Again, a successful example is a company like Recursion. They can image hundreds of millions of cells that are stained in a special way, and they can subject them to chemical and genetic perturbations to see how drugs affect them. But I think the future step, or the direction in which we would like to look ahead, is to develop purpose-built new modalities, or maybe repurposed old modalities, so experimental techniques, to produce ML-specific data for problems where we have this special structured degenerate solution space, and we will probably need to give up to liberate ourselves from these constraints of a human that has to look at the data and co-develop ML and experimental technology. And let me give you one example. So from the problem of proteins. So this is a work that I do with a company called VantAI, and it's a company in the business of molecular glues. So molecular glues are small molecules that induce interactions between proteins that normally do not interact. And the claim to fame of this company is structural proteomics. So it's experimental technology that produces structural interface data between proteins up to 6 orders of magnitude cheaper than traditional X-ray or cryo electron microscopy. So you basically get a protein interface structure for the cost of a cup of espresso, right? Where the traditional techniques can cost hundreds or sometimes even millions of dollars. So, of course, it's not a full 3D structure, and on its own, this data historically has been considered too sparse to allow the direct inference of structure, but it is very cheap, it's a very high throughput, we can collect millions of these samples, and when it's used in conjunction with specialized, appropriately developed generative ML algorithms, it is sufficient to produce meaningful results. And what I show here is a result of protein docking. And I should also say that in biology, this unlocking of new insights by moving away from human processable data is not exactly new, and if you trade off data interpretability for exponential increase in scale, it was really the key to probably one of the biggest achievements in biological sciences to date, which is the Human Genome Project. As you probably know, sequencing of the human genome was made possible by a technique called shotgun sequencing. It was proposed by Craig Venter. Basically, it smashed the DNA sequence into millions of human unintelligible, you can call them black box pieces, that were then reassembled using alignment algorithms. So there was no deep learning yet, but it was a computational approach that was developed together with the experimental technique. And in computational photography, so this is actually a field that my brother Alex works on, traditional imaging systems basically produce the data of the type of what you see is what you get, right? So when you want to take a picture, the data that is captured by a sensor will look like a picture. maybe with some artifacts, with some noise. But in modern imaging systems, something that you see on your iPhone, first of all, you see that there are multiple sensors. And the input data doesn't look like the final outcome. So all these different data sources and data modalities are fused together into something that looks like a much better picture that is achievable with one of these sensors. So again, it's a kind of black box data, and you can also find some crazy exotic sensors like event cameras where the input doesn't look like an image at all. So it's a megahertz sequence of changes in pixel brightness at different positions. Now again, we use black box term as some kind of pejorative for something that we don't understand, but I'm not suggesting that AI has to forgo all the scientific knowledge we have acquired so far in favor of purely data-driven techniques. And I think quite the contrary. In the past years, we've seen a trend of combining mathematical equations that are specific to a particular domain with general purpose machine learnable components that are trained on experimental data. And these approaches are sometimes called physics-inspired learning, or I like in biology a term that was introduced by my colleague Mohamed El-Kirashi from Columbia, differentiable biology. So basically you bring the machine learning terminology to biological systems. And we've seen that geometry offers a powerful framework to formalize some of these primitives through the language of symmetry and invariance, right? And we nowadays see some of these techniques used in chemistry, in physics, in the form of invariant and equivariant architectures, of which AlphaFold is probably the most famous and successful example. So we have a Goethe-themed evening. So I started with a quote from Goethe. I think I need to finish with a quote from the great German poet. And you know him as a poet, but probably it's less known that he was actually a scientist, or a natural philosopher, as scientists were called at that time. And he studied in Strasbourg with Jacob Spielmann, who was one of the last alchemists. So that was the time when chemistry was rapidly, alchemy was transitioning into real chemistry, into real science. And Spielmann was one of the last chemists to believe in Encheresis Naturae, the hand of nature, kind of semi-magical force that supposedly breathed life into living things. And Goethe was apparently very unhappy with this simplification, so he put in the mocking mouth of Mephistopheles in the famous scene from Faust, this term, Encheresis Naturae, is the chemical name by which dunces themselves unwittingly shame. And it's been 250 years since. We now have a much better understanding of biology. We don't need to resort to any magical forces. And in some cases, we're able to trace interactions between molecules to effects on cells. And in some cases, it has given us drugs against diseases that just maybe a few decades ago would spell a certain death sentence for the patient. And yet we still lack a systematic view of connecting different biological scales, especially translating the knowledge of the low-level molecular processes to the functioning of cells, tissues, and entire organisms. And while I'm enthusiastic and very excited about the capabilities that AI technologies can bring in biology, I'm worried that overly optimistically entrusting AI with somehow solving biology is, in a sense, return to alchemy, and this time as Encheresis Machine, the hand of the machine. And as I said in the beginning, I hope I have convinced you also in this talk that the path to biology 2.0, right, so the new AI first version of biology lies both through GPU clusters and the wet lab. And it's necessary that biologists and computer scientists work together on the next generation of machine learning and experimental technologies. So I invite you to join forces with us at AITHYRA, that I hope will be an amazing ride here in wonderful, beautiful Vienna. Thank you very much.
Well, thank you, Michael, for this very you should get used to the quality of presentation and to these insightful talks. I think this was really insightful and also trailblazes the future of the institute. We have about 10 minutes for a Q&A session, maybe slightly less. Any questions in the audience? Please, yeah.
Thank you for the visionary talk. In the context of protein folding and convolutional neural nets, for example, you have the notion of symmetries like translational invariance and equivariance. But if we start thinking about like higher order scales of biology, like the transcriptome, proteome, up to the point of organisms operating in an environment, do you imagine that the symmetries that we would be able to apply in those higher order contexts would emerge if we find the right coordinate transformation of that data space so that we can reuse the symmetries that we know? Or will we have to discover kind of new symmetries, like new equivariances and invariances?
So it could be something much more abstract and category theory that was developed historically as the follow-up to the Erlangen program of Klein in the 1940s. Basically offers a language that allows you to abstract, so to talk about basically structures of relations. So there are some efforts that try to take equivariant architectures to this direction. So it allows exactly to talk about, for example, what are symmetries in software code, right? Which is not necessarily a purely geometric structure. So I believe some of these methods might be interesting to try in biology as well.
There is a question over there.
Thank you for the fantastic introduction. I really like the idea of the black data. So we all know, like when we train a model, like garbage in, garbage out. So like, for example, OpenAI, they value a lot on data quality. They spend a lot of money to create high quality data. So do you have any insight on how we do data quality control in this black data model?
Yeah, so this is a very good question. So I probably the answer, I have limited times, but I think it's fair to say that even OpenAI, most of the data on which ChatGPT is trained is noisy data. So they have a small subset of high quality data and reinforcement learning with human in the loop. So probably that would be a way to do it. What is probably also important is that, and this is probably also, well, kind of complain about the way that academic system and the industry operates. What is more important for machine learning arguably is negative data rather than positive data. And this is something that we don't find. So if you have a failed experiment, you don't publish it. If it's a project that didn't work in a pharma company, then you will never know about it. And this is probably the most useful data that could be utilized by machine learning. So we should rethink the way that we treat unsuccessful experiments. That they will be very, very valuable and very useful.
Hi, thanks for the talk. Based on your very beginning slide, that biological questions encompasses from molecular scale all the way from population. And how do you exactly envision AITHYRA to focus on? Especially from computational perspective, like regardless of linear RNA protein, they can share pretty much the same primer. But experimentally speaking, like these bases are really different, how you're in the lab. And so as an institute, what exactly are you planning to tackle next?
Yeah, so we cannot tackle all the scales, right? So a very big institution like the Broad Institute, for example, this is probably what even they cannot afford looking at all the scales. So we'll probably start with smaller scales where we have better understanding, and we'll partner with other institutions to go to higher scales. But at this point, I think we will be pragmatic. So I think what is more important is which problems are likely to be solved by or solvable by machine learning techniques. Because there is plenty of problems in biology that can be addressed by these methods. We need really to focus on the right ones. It's difficult to predict what will be the right one, but we want to find hard problems, important problems, and problems where we can generate data experimentally, maybe simulate. So simulations are also very interesting. So traditionally simulations, right, at least for problems where we know the physics and the governing equations are simulated with numerical solvers. So there is interesting research direction where these will be replaced by generative machine learning models. So this potentially could, if it's successful, it could have a huge impact on all fields of computational science, right? So from molecular dynamics to weather forecasting, right? Fluid dynamics. So of course it will be a very different way of doing things, right? So you will be generating data, generating predictions that in some cases will not make sense, but it's very easy to test whether your prediction is garbage or not in some situations. Yeah, so I think we need to be open-minded and prepared for doing things very differently from what we are used to.
Martin first.
Yeah, thank you. Great talk. So you talked about pictures and 3D structures of proteins, but you didn't talk about videos and movies or the fact that biological systems are dynamic systems. So where do you see machine learning in the institute or in the future in dynamic systems, especially where we still lack many basic mathematical tools?
Well, so the example of molecular dynamics, right? So this is probably a very, very good example. So these are very heavy, traditionally very heavy computational solvers that try to simulate how a molecule moves over a scale of nanoseconds. But one of the limiting factors is that the step size of these simulations must be of femtosecond scale. So again, you have orders of magnitude of gap that you need to bridge, and this is one of the reasons for the inefficiency and the poor scalability of these approaches. So if these can be accelerated or even replaced with some forms of generative models, this will be a huge breakthrough. So obviously we are not the first to think of it, so there are companies that try to go in this direction. Isomorphic labs, from some rumors that I'm hearing from insiders, including former students. They don't publish or speak much, but that's likely the direction that they go. So they try to simulate data for the future versions of AlphaFold and similar things.
But you need high throughput sources of dynamics data, which is a big challenge, of course.
Yeah.
So there was another question here.
Yeah, also from me, thanks for the great talk. I also really like the idea of the black box data, and I think I can see the potential of it. But I also wonder, like, at some stage, you need to introduce interpretability for the end user. Otherwise, like, the deep learning models will create awesome representations, but we can't do anything with them. So do your theoretical considerations of this framework already include ideas of how these tangibility for users comes in?
Yeah, so black box data is not necessarily antithetical to interpretability. So in general, deep learning methods suffer from interpretability, so it's probably a trade-off, but it's not necessarily a binary trade-off, right? So it's not that either you have interpretability or you don't have. So you can still have somewhere in the middle. So you'll probably need to give up some interpretability in exchange for scale and maybe accuracy and efficiency. But it doesn't need to be either you have it or not, right? And of course, there are some techniques that try to solve the interpretability question. So I think, well, one of your colleagues at ISTA, Locatello, is working on, for example, causal inference. So that's potentially one interesting direction. Yep.
Question here? Oh, sorry. There.
Thanks. Continuing along those lines, more and more parts of the process are now becoming black, so to say, or uninterpretable or machine guided. What other parts do you think could or should potentially become more machine regulated, and where would you draw the line and why?
So I believe that it is very possible that the science of the future, and could be actually very near future, will be done by machines. So the hypothesis generation that traditionally was given to the human creativity, ingenuity, some spark of insight, eureka, can be done by a machine. So probably the first where we will see it will be maybe paradoxically in pure mathematics, because you don't need to deal with experimental data, right? So you can formalize your theorems in some abstracted logical way, and then you can produce new results. There are some efforts that try to build AI scientists. So one of them is Future House in California, that I'm actually going in 2 weeks' time to meet. So they're doing some interesting things. So this is also a direction that we would like to explore. So they're betting on large language models. In my opinion, it's not necessarily the right architecture for every problem, but I think the direction itself is very interesting.
Congratulations. Great talk. Is it working?
Yep.
Now it's working.
I have a more practical question. Since it's the birth of a new baby in Vienna, and the baby has to be educated, and I'm curious, how fast will the baby go? And will it be co-educated between Oxford and Vienna? Or what kind of vision do you have to make this a success, which we all would like to see?
So probably the answer I can give here, so we'll try to move fast, but we'll try new things, and we'll see what works, what doesn't. So we want to be agile. So I take it as a kind of startup mindset. So we definitely would like to build links with Oxford. So I would like, for example, to have a joint PhD program, maybe with other institutions as well. So we want to bring maybe more of the machine learning spirit to these more traditional scientific fields. So the spirit of moving fast, breaking things. Well, of course, not breaking to the extent that it can do harm, but yeah, basically something that has been the driving force of this field that made it so fast and so successful. For example, the open source community that was very efficient in machine learning would be very beneficial for biological sciences as well. But to education, basically, we do want to contribute to education of new students, in particular to students that are skilled in both fields, in life sciences and in mathematics and in computer science.
I would like to abuse my higher location here to actually challenge one of Michael's claims. He invited harsh criticism, so here it comes. So actually, I think AlphaFold is not an example of a thoughtless black box that completely replaces a scientist. I think it is actually based on a very ingenious, a very deep observation of coevolution of structure that was made really a few years before the AlphaFold breakthrough came. So that insight, that eureka moment that allowed AlphaFold, and not the brute force availability of data, because frankly we don't have enough structured data to train the ImageNet-like regressor. That would be impossible, but actually the availability of another unsung hero, the availability of structured data without sequence data without structure that was made possible by Craig Venter and other, that is the driving force. So I don't think AI will replace human scientists in the foreseeable future. That's my opinion.
Well, I might disagree with this, but this is true. So, and the better example is the successor of AlphaFold, so a different, a parallel project that was initially developed by at Meta, and now it's a separate company called Evolutionary Scale, so the ESM fold. So it forgoes entirely the structural data, but it's trained on significantly bigger amount of sequence data, so basically the coevolution, and this is a protein language model. So there is enough signal apparently in multiple sequence alignments to predict structures probably less accurately than AlphaFold, and it doesn't solve all the problems that AlphaFold can solve. But yeah, there is a lot of in the data, and this is related to the point that I mentioned, the intrinsic structure, so the distributional hypothesis that we have in this data. So it's definitely not thoughtless. It's very carefully engineered.
I think probably last question, right? Because we're running out of time. Over there, please.
Thanks for the talk. I want to ask about these primitives that you mentioned. And usually, at least my vision of the field is that whenever there have been efforts in trying to explicitly get these primitives of different tasks, the success has not been that high. Whereas kind of throwing data, the right models that have the right inductive priors have worked. What's your point of view on this, and why do you think that we've struggled in getting the composition right?
No, I'm not sure that I understood perfectly the question, but what you're saying is that certain types of inductive biases work and certain types don't work, and you don't know when, right? Basically, when this will be the case. So I would say that the priors that come from physics that we really understand that exist in the problem, and I think in case of proteins we definitely have this understanding, right? So all the geometric symmetries, we know that they are there because that's how the physics works. This is an obvious thing to put in, whether you hardwire it into the architecture or you learn it with something that is just big and powerful enough, like a transformer. This is what AlphaFold 3 does. That's a different question, right? So data augmentation is still a valid way of learning inductive biases, right, or imposing them in the architecture. So, but in order to do it, you need, of course, to understand what is the right structure that you're trying to impose. So there are works that try to learn symmetries, I would say, with moderate success in some problems, but I think it's still an open research question.
I think we'll stop here, and of course Michael will be available offline
I'm happy to discuss at the reception that follows the talk.
Thank you, Michael. Thank you very much.
Thank you.
Ladies and gentlemen, Professor Bronstein admitted that he is a big opera fan, and not only are they geniuses at what they do, but having this baby in Vienna is a very good move and a genius move for all those of you that like opera. There's two very famous composers for the opera Faust. One is Gounod, and the other is Berlioz. I like the Berlioz version more because it's crazier. And the first sentence I will sing is exactly what you were saying. Nature immense, impénétrable et fière. Incredible nature, impenetrable and proud. All of this talk, which I found fascinating myself, I have to tell you that we must never forget to look at great art also as a warning sign, I believe, because don't forget that Faust makes what seems to be a great deal. Eternal life, eternal beauty. He gets to rule over nature. The problem is, he makes the deal with the devil. And by all rules of nature, and probably by your black box, it's a bad idea. So, I'm looking forward to finding the good, and maybe you'll find it in your boxes. It is fascinating to have been here this evening. Thank you very much. Impénétrable et fière. Toi seul, ton rêve, oh mon ennui s'en va. Sur ton sein tout-puissant, je sens moi ma misère. Je retrouve ma force et je crois vivre enfin. Oui, souffler fade, crede, oh Adam, t'aura précipité vos ondes, à vos bruits souverains, ma voix aime à s'unir. Forêt, rocher, torrent, je vous adore, monde qui sentirait vers vos silences le désir d'un cœur trop vaste et d'une âme altérée, d'un bonheur qui ne fuit.